Our fourth demo talks about kinetics. It's a very complicated topic, but it's so much easier to grasp when you're playing with kids and playing with cars. So this is a really good demo to understand kinetic and potential energy. We already discussed a little bit about a battery. A battery is a good example of potential energy. It's stored energy that's there and available to be used later. Well, rolling cars is a great way to learn about potential and kinetic energy, and it's a great way to incorporate some math concepts while you're at it. So inviting is no problem. I invited my dog to help me participate when I was rolling cars around. But talking with kids and supporting them and explaining to them what's happening and encouraging them to guess what's going to happen and then do the experiment and observe. That's where a lot of the learning happens here. There's also a lot of document taking and a little bit of math and different levels that you can take this as far as explanation goes. And the slides provide all those options. So there are a lot of standards that are covered here through this experiment. So I highly recommend doing it. Again, you learn a lot about science and math. As far as safety issues, as you can see, I don't have any glasses on. Perhaps knee pads would have been appropriate for me, but the kids don't seem to have any safety issues around this. It's important that kids understand for this experiment that the cars should not be pushed in any way. You're basically holding them and letting them go for this experiment. If you push them, then you change the statistics of their behavior. And then it's really hard to measure what's going on. Another really important thing for this particular demo is to set up groups where you have tasks. And then you rotate the tasks. That keeps kids on task and focused as to what they should be doing. If you have a lot of different people rolling the cars, you'll find that you get a lot of different data. As far as equipment, what you need here is cars, and I've tried a bunch of different kinds of cars. The main criteria is that they roll fairly straight. Once they get off the ramp, they roll fairly straight because we're going to be measuring the distance from the bottom of the ramp, and if they flip over or veer strongly to the left or the right, then they become outliers, and we'll talk about that later on. Also, you're going to want to make sure there's not a lot of hair on your floor or other garbage that could get caught up in the wheels. That makes things very unrepeatable. We've had that problem happen too. You're going to need 2 items that are 2 inches or less. In the classroom, I never have a problem. We just pick 2 books and make the books identical because you need a height 1 and a height 2, and they have to be identical. So your height 2 should be twice as high as your height 1. It's good to have a ruler. In the classroom, it's really nice. Almost every classroom floor I've been in has the 1-foot squares. So you can count how many feet the car went and then add on the extra inches. For doing these measurements, we like to keep everything in inches. So if it went 1 block, it went 12 inches. But as far as materials go, Matchbox, a couple of these Matchbox tracks, and then I used a flat piece of cardboard because the tracks sag in the middle, and so it messes up your numbers. So we talked about the heights. 2 inches should be your max because once you get it too high, the car starts veering and it messes up your numbers. And we're sort of at the edge of the height I'm comfortable with working with. So for this experiment or demo, we start out with a hypothesis. Kids are funny about this because they have to guess and they don't want to be wrong. But that's the nature of curiosity. You have to guess, and that's how you learn. When you guess right, you remember it better because you're like, hey, I guessed right. I'm so smart, I'm going to remember that. When you guessed wrong, you remember it better because you're like, darn, I didn't guess right. You know, how can I guess better next time? But in the end, it's still a guess, and if you make it, you'll learn so much better. So let's start with hypothesis 1. It says the distance a car rolls depends on the height of the ramp. So kids are going to say yes, kids are going to say no, and then you do the experiment. And that's the nature of chemistry and science. So you may have noticed that I'm not starting with an entirely flat ramp, and that's partly because I'm going to start my measurement at the bottom of the ramp. And I'm using this ramp just to convert potential energy, which is the height. Whenever you hear height, you're talking potential energy, to kinetic energy, which is the energy that the car will have at the bottom of the ramp when all the height is gone. And then we can measure that. We can't really measure the speed of the car at the bottom of the ramp. That's really hard to do. But we can measure the work that is done by that kinetic energy. And that work, so the speed at the bottom of this ramp will determine how far the car goes. So we can measure the height at the top of the ramp and the distance that the car goes. So in order to start out, we kind of want to make up for all the friction on the ramp. So we kind of want the car to go to the bottom of the ramp. Boy, that worked out really well, actually. Ideally, you want it to stop at the very bottom, and you consider that 0. So that height is the height where the car has no kinetic energy at the bottom. It turns out it's higher than flat, but that's only because you need a little height to get it to the bottom, and you're making up for the friction. So this is considered height 0, and it didn't go any distance. We consider that distance 0. So we're going to start with height 1, and we are using a brownie cake batter mix as our height 1. Again, this is probably kind of high for height 1, but a book is good. A classroom book is good. And so I will scoop this up. The really good thing about this is you can divide your group into teams, and I recommend like 4 kids per team. And you can see there's a lot of things to talk about, and that's the great thing about doing an experiment. So the idea is we have a height now, and this is height 1. And I've been rolling cars all day. You may have to do some pre-work, but you want to pick a car that rolls fairly straight, and then you want to pick a car that weighs the exact amount as that first car. So I actually got duplicate cars because I'm doing a car and then a car that weighs twice as much. So the way the car rolls depends a lot on the tires and the balance of where the tires are relative to the other weight. So you don't want to skew your experiment. You want 2 identical cars. This red car and this red car are the exact same. I taped another car on the top that weighs the exact same as that red car. So this car weighs twice as much as this does. But it has the same kind of tire system. So it rolls about the same. And that's really important for getting this data. It's not essential. I mean, you'll still get reasonable data, and you'll still be able to answer your hypothesis. But it's really good to talk with kids about doing things repeatedly in the same. So our hypothesis is the distance a car rolls depends on the height of the ramp. So let's roll a car. Here's a ramp, and we're calling it height 1, and here's a car, and we're going to roll it. Okay, now there's a question. Do we count that roll because it turned at the end? Or do we re-roll? And there's no loss either way, but we'll go ahead and look at it. And it appears to be about, and you have to decide where are you going to measure it and where are you going to roll it from. So we rolled it where the back of the car was up against here, and we're going to measure it at the back of the car. So it looks like it's about 22.5 inches, but it did turn. But we're just going to say 22.5 inches, and then we're going to put an asterisk by it and say it turned. 22.5, and the asterisk means it's not such a good data point. So let's go ahead and see if we can get one that doesn't turn. Okay, this is at about 23.5 inches. So let's write that down. It doesn't have to be completely accurate. And it went straighter, so you can kind of decide how straight you want it to go. Okay, and that went, the back of the car again is at 23. You have to agree, because if you measure from the front of the car, it says 25.5, and that's different. So we have 23. So it looks like that first data point, even though it turned, is pretty close to the others. But we'll get one more. Okay, and this one went a little further. It went like 24.5, and it went straighter too. So we needed 3 data points, and we can decide 22.5, 23.5, 23, and 24.5. So we've got a number of data points, and the average is about 23.75. And so that's about the distance the car rolled at height number 1. So let's figure out, does it roll further or doesn't it? And it depends on your guess. I might have guessed, because I've done this before, that the higher the ramp, the further it would roll. And most kids will guess this. So let's see if I can do this without tipping it over. All right, let's see what we got here. All right, so here's our car. And let me scoot this a little bit closer so that ramp gets a little bit more support and doesn't sag so much. And we've been using this ramp, so we're going to use this ramp again so we have repeatable results. Whoops. Well, that was, it ran askew. Let's see if we can't get one that goes straight here. All right, well, that went fairly straight. Let's see how far it went. It went to about, I'm just following the line on the floor. So it went to about 45 inches. So let's get our first data point down there. You can see I didn't even write down where it crashed into the side. And that's a skill set. I mean, that's for math. You need to understand when you have an outlier, where you have a data point that's so skewed that it's not representative of what you would get normally. So I'm holding it from the bottom there. All right, now that turned a little, but let's see where it ended up. It ended up at about 40. So I'll put an asterisk by that, and we'll see if we're going to count that or not, depending on if we can get some straight ones here. All right, now that ran over this. It could have slowed it down, but the back is still at about 40. So let's see, we'll add another 40, and I'll actually take this tape off so we don't have that problem again. Kids love this. I love this. All right, whoa, that one went pretty far, huh? That one went about a finger into, so that went, here's the line. So that went about 43.5. Okay, 43.5. And it's kind of up to you, since that one went fairly far. I got a 45, 43.5, and 2 40s. Let's do one more and just see if we can't. Okay, well, that one definitely turned, and that one's way in the 30s. So I'm actually going to count that as an outlier. I'll write it down. It's 34, but I think it's an outlier. So I'm still going to, so I'm asterixing it. So the ones I'm worried about, I put an asterisk by. Okay, that one I'm not even counting. It definitely turned. So let me double check that this thing is lined up straight. All right, and that one went straight, and it's at 40, about 44. So, okay, so we look at the numbers, and it's a great chance for your kids to talk. They can decide which ones they want to count and don't count, and why. You can not count numbers, just explain why you didn't count them. You can't just get rid of data points with no reason at all. Here our goal was to have a straight line, so ones that didn't really do a straight line, we probably won't count. So we end up with 1, 2, 3, 4 data points. And if you average them, I'm going to have to wing this. So 5, 6, 7, 8, 13 divided by 4, 12 divided by 4 is 3. So it's about 43. So if you guessed that the distance a car rolls depends on its height, if your hypothesis was yes, then we confirmed your hypothesis. At the shorter height, it went 23 inches. At the higher height, it went 43 inches. And you can imagine there's a lot of discussion that can happen. Different folks could have different cars. The idea is, in the end, your classroom's going to have to agree on the hypothesis and what they discovered. I included a chart here you can use to fill in sort of how to set up the ramp. I talked about the optional 0, which is what I did to make the car just stop at the end. You'll still get the same general result, which is yes. The car rolled twice as fast down the ramp because the ramp was twice as high. Don't forget, height always means potential energy. So if it's twice as high, it actually has twice as much potential energy. And that's converted to kinetic energy. So if we could have measured, the car that's twice as high would have been going twice as fast at the bottom of the ramp. And it should have gone twice as far because that kinetic energy can be converted into work, which is force times distance. We measured the distance. So a car going twice as fast goes twice as far. So if it's twice as high, we should have seen it go about twice as far. And we kind of did. It went 23 inches, and when we made it twice as high, it went 43 inches. So this is a good confirmation of what we know, and it's also a good confirmation of the hypothesis. Okay, now the next few slides I have could be for different age groups. That may be the end of the discussion, and that may be the end of the experiment. But I have a few more slides, and they involve math. So height, the H, is always potential energy. And potential energy can be converted directly into kinetic energy. And that's what they want you to understand, the difference between height, which is potential energy, and speed, which is kinetic energy. Kinetic energy is always the energy of motion. And in this case, for our experiment, we couldn't measure how fast the car was going at the bottom of the ramp, but we could measure how far it went, given the speed it had at the bottom of the ramp. And that's the D here for distance. So that explains why the height is going to match your distance. If your height is twice as high, it should go twice as far. And it's simple math. In fact, it's physics. If you have a group of 6th graders, they should understand this math. So your height is proportional to the distance it went, because the potential energy equals the kinetic energy, which then should equal the work that's done. So again, you can go over that in whatever detail you want. But let's move to the next hypothesis. Will the car that weighs twice as much roll further? We're not even saying twice as far, we're just saying further. This is a great hypothesis, and your kids should guess and talk about why. This is a non-obvious experiment because it won't roll further. And so I guessed that it would roll further. It makes perfect sense to me it would roll further. But it has to do with the way this experiment is set up. And we'll talk about that when we go. But I talked to you a little bit about how you make a car weigh twice as much. I super glued beans on here. I did all kinds of things. But the easiest way by far is to tape another car upside down on top of your first car. That way you have the same rolling dynamics. And make sure that your second car weighed the same as your first car. And make sure that you don't tape them in a way where they're skewed. Try to tape them so that the car on top is centered, kind of in the middle, So that will greatly impact the way your car performs. In fact, it might flip over if you tape it in a really funny way. So let's start at height 2 because, well, let's start at height 1. We don't even need to do different heights for this experiment. So, but the experiment works either way. But if you start at height 1, so you can use the same, you can roll them at the same time if you want, or you can measure them. Either way is fine. So let's roll them at the same time and see what happens. And then we can measure them and see what happens. And it helps to have a couple of kids and you let go at the same time. It helps when they don't crash too. So it looked like the heavier one went a little bit further. But it looked like the lighter one went about 21 inches and the heavier one went about 25 inches. So this is car 2, height 1. So car 2 is the heavier one and it went about 25 inches. We'll say car 1, height 1. And it went about 21 inches. So this is really important to talk about because there's a lot of variation. So the first thing you would want to do is switch ramps and see if that matters. So this time we'll put them on different ramps. And it looks like the red one went to 24 inches this time. So car 1 went to 24 inches. And the heavier one went to 25 inches this time again. So now it's just a question of gathering a little bit more data, which is always fun. Let's switch them again. Let's run them both down the same track and just see. And then hopefully they won't crash. Okay, so again, the heavier one went a little bit further. The light one went 23, and the heavier one went 24 and a half. 24 and a half. Okay, and let's switch them again. Or let's just do this one again. Now, there are things you can do here. Like I'm trying to start it in the center, but it could hit an edge. Oh, well. So this second piece of data got skewed, and my first one got knocked a little bit. Let's see if we can do it so that it doesn't knock them. Okay, so the lighter one went about 23, and the heavier one went about 24. 23. Okay, so we've got some data point, but the take-home message is you average them. So 21, 24, 23, and 23 is 6. It's 11 divided by 4. It's almost 12 divided by 4, which is 3. So it's just shy of 23. It's like 22 point something. And then the heavier car was 25, 25, 24 and a half, 24. So it was really close to 24 and 3/4. So it was really closer to 25 on average. And so if you were to say, did they go the same? Compared to these two, you know, the car that weighed twice as much did not go twice as far. So I would say they went pretty similarly. And this is where you have a good discussion because I didn't take into account the weight of the tape, which may make that system weigh a little more than twice as much, which may explain it going a little bit further. There are a lot of things you can talk about, but you can say the car that weighed twice as much did not go twice as far. And that's what I intuitively expected because the height that was twice as high made the car go twice as far. So on the hypothesis here, I'm going to have to say the answer is no. The car that weighed more may have rolled twice as fast down the ramp because it weighs more. So the car that weighed more, at this point in time, this car may have been going twice as fast as this car, right as it went down the ramp. But the problem is that to move this car from here to here, it's like moving a wheelbarrow that has, one pile of rocks versus 2 pile of rocks. It requires more work to move something heavier. So the potential energy was more because it weighed more. The kinetic energy was more because it weighed more. But it didn't go any further because it had to do more work because it weighed more. So this is where, again, it depends on the age group of who you're working with. But in this case, only the mass was different. So the potential energy, which is height, right? Don't forget potential energy is height, equaled the kinetic energy, which is the speed. The height converts entirely to the speed at the bottom of the ramp. But the distance it went also depends on the work that was done depends on the mass. So when your mass is more, so we'll pretend that yellow is the car that weighed double. When your mass is more, you have to do more work. So you end up going the same distance. So when your mass is more, you have more potential energy up here, and you have more speed at the bottom of the ramp. But it didn't go any further because you have to do a lot more work to move things that are heavier. And that makes sense too. So it's a tricky concept, this hypothesis too. For 3rd graders, you can just skip it all together if you want. But for 6th graders, it's important to make a guess and be wrong and try to figure out why. Figure out what makes sense and try to understand the logic around it. So this is the potential and kinetic energy demo. And the take-home message is, whenever you see the word height, it's potential energy. Whenever you see the word speed, they're talking about kinetic energy.